Lab 4, Oscillations, and the purpose of this lab is to observe two-dimensional motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. And these are all the equations and constants relevant to this lab and observing the motion and then subsequently modeling it. So there's the fundamental principle, final velocity equal to initial velocity plus F net divided by m times delta t. There's the formula for kinetic energy, the potential energy of gravity, potential energy of the spring, change in potential and kinetic energy. There's change in position, final position is equal to initial position plus V average over time plus times delta t. The force of gravity, force of the spring, and F net, which is the sum of all forces. And so in this lab, there's the force of the spring and force of gravity acting on the ball. The constants, gravity, 9.8 meters per second squared. The length of the spring is 0.123 meters. The spring constant is 6.83 Newton meters. The initial position of the ball before it's released and set in motion. And the mass of the ball at 0.402 kilograms. And the data was the video was put through Tracker and modeled and plotted. So here we have the X position plot, the Y position plot, a spreadsheet of the data, and the actual video itself. And subsequently, using the equations from the second slide from earlier, that data or a computerized model can be built to create a simulation of the motion. And what it creates is this simulation of the ball in motion, and the blue line here is just the path the ball is taken. The black arrow is the force of gravity, and the blue one is the force of the spring. And over here in this graph, the change in kinetic energy is the blue line. The change in potential energy due to gravity is the red line. The change in potential energy due to the spring is the green line. And the total change in energy is the yellow line, which is, notice that it's 0. And then this is subsequently, after making slight tweaks to the code from earlier, you can I modeled the position time data of the actual ball in comparison to the model. And as you can see, they line up pretty closely and touch, and there's a large amount of overlap. So the oscillation period, the horizontal period of oscillation is 1.62 seconds. The vertical oscillation period is 1.52 seconds. These oscillation periods are different because the oscillation in the horizontal direction is pendulum motion, and oscillation in the vertical is due to a spring. And these are, while they appear similar, it's two different types of motion, and the equations for time period for the two different types of motions are different. And so while a lot of the numbers are the same for them, you're going to get slightly different answers. And going back to the energy principle and this motion satisfying it, the change, the energy of the total system is 0 because our system is the spring, the ball, and the earth, and no new energy is put into the system or taken out of it. It's just all converted, and it bounces between kinetic and potential energy as the ball moves around. And it's either at a point where it has maximum kinetic energy and no potential, or maximum potential and no kinetic at different points in its motion. And so in conclusion, the system of the spring is the spring, ball, and earth, and subsequently change in energy is equal to 0. No new energy is put in or taken out. Energy changes from potential, kinetic, and back, so it satisfies the energy principle. And the horizontal period of oscillation is 1.62 seconds, and the vertical is 1.52.